we're going to look at this example. This is the last example in our class notes from section 1.2. So we're given this description here, and it does not really ask us anything specifically about a differential equation. But what we're going to do is use a differential equation to model this situation and then use the solution for that differential equation to help us answer what it actually does ask us. So we want to make sure that we're exhibiting all those good behaviors, good practices for using differential equations to model situations. So first of all, we want to clearly state our assumptions. That's done really in the problem here for us. It gives us some information about the situation, and then we have this assumption that we have this constant deceleration. And then we want to think about variables. So in doing that, you want to identify where is the rate of change that it's talking about here. So really the rate of change is here where it's talking about acceleration or deceleration. So acceleration is rate of change of velocity with respect to time. So that would tell us about dependent and independent variables here. So we've got a dependent variable, velocity, and that's a function of time. So we want to be a little bit more explicit about how we actually are describing these variables. We want to talk about units and velocity of what, when, and what time we're talking about here. So we've got the car traveling along, and then all of a sudden the brakes are applied, and so the question is really asking us about what happens after the brakes are applied. So we're going to measure that time, and we could choose to use whatever units we want here, but I'm going to use seconds since I've got some measurements given here in feet and feet per second after the brakes have been applied. And so the velocity would be measured in feet per second of the car at time t after the brakes have been applied. Alright, so we're going to go ahead and write down a differential equation here. So we have an assumption that the braking system provides constant deceleration. So that tells us that our assumption is that the rate of change of velocity with respect to time is some constant. And so I've used c there to represent that constant. So that's really another thing I need to describe here. That's a parameter. Notice I'm kind of going back and forth between writing the equation and then describing my variables, so that's a pretty common thing here. And the units on that would be in feet per second squared. So rate of change of velocity with respect to time. So feet per second, or feet per second squared. Alright, so there's our differential equation. We've got some initial conditions given here. So at the instant the brakes are applied, the car is traveling 60 miles an hour or 88 feet per second. So that tells us that at t equals 0, the velocity is 88. That's one of our initial conditions here. Alright, and then the other piece of information that's given here is really about how far the car skids. And so that's really about position. And so we've got this relationship that rate of change of velocity with respect to time is acceleration, but we also have a relationship that velocity is rate of change of position with respect to time. So I do have a second dependent variable here. I'm going to use x to represent that. So position or distance the car has traveled, and we're going to measure that in feet, t seconds after the brakes are applied. Alright, so I actually have another value here. The other piece of information here, sometimes students will look at this and say x of 0 is 176, but the car has not traveled 176 feet when the brakes are applied, so that's not actually correct. So it travels 176 feet before it stops, but at the instant the brakes are actually applied, the car hasn't traveled any feet at all. So x of 0 equals 0. It hasn't traveled any feet since the brakes were applied at the instant the brakes were applied. So that's kind of a hidden initial condition in there. You have to be careful of when you read the problem and think about what those numbers actually describe. So what is the 176? Well, the 176 is how far the car skids before it comes to a stop. And so there's another kind of hidden value in this problem that it's asking us about. We need to know how long it takes until the car stops. and that would be measured in seconds after the brakes are applied. So that's really a parameter because that's a constant value. I don't know what it is, so it's an unknown constant, but x of capital T is 176. That's really what the 176 tells us. The other hidden value in this problem that's going to be useful is that when I think about what is going on with position when the car stops, I also know something about what's going on with velocity when the car stops. So at that time when the car stops, the velocity of the car would be 0. So there's another hidden condition in the problem there. Alright, so now I've got my differential equation, I've got my initial conditions, and then these other sort of ending conditions, sometimes those are called boundary conditions, written down, and then we can go ahead and solve the differential equation and answer the question. Alright, so the differential equation is one of those easy kind that you saw in Calculus 1, where you've got the derivative of a function and you want to recover the original function. So we want to recover the velocity function as a function of t. So I'm just going to use an indefinite integral to undo the differentiation. So I'm going to integrate that with respect to t. And so I get ct plus another constant. I already used c for a constant, so I'm going to need to use something else. I'm going to use k for my constant here. So there's a solution to that differential equation. I do have an initial condition that will allow me to find k. So when t equals 0, v is 88. And so I can write down my velocity function. And so there is the solution to that first differential equation, rate of change of velocity with respect to time. I do have an unknown constant in there, which at some point we will actually be asked to find. It actually asks us to find that as part of the question. What is the constant deceleration? All right, we're going to go ahead and write a second differential equation. So remembering that acceleration is rate of change of velocity with respect to time, and velocity is rate of change of position with respect to time. I can write a second differential equation here. So dx dt equals, and I'm just replacing my v of t with dx dt, so ct plus 88. And then I can go ahead and again undo the differentiation that's in this problem. So if I want to recover the x function, I'm just going to integrate this with respect to t. And then I'll have another constant here. So I think in my notes I used p probably for position function, but that's a constant of integration there. I do have an initial condition here. So we know that at t equals 0, the distance traveled is 0. So we get that p equals 0. So we've got our position function here. X of t, 1/2 ct squared plus 88t, and the p is 0. So there is our position function. Okay, then the other pieces of information that I've got here is at this capital T, that is the ending time when the car stops, I've got velocity and position for that. So I can use those to find what is that capital value of t, and then the other thing it asks us to find, which is what is the value of c, the constant deceleration. All right, so I'm going to plug my other conditions, my ending conditions, into the appropriate equations, capital T in for t, and then 0 and 176 in for the outputs of those functions. I'll go ahead and write that down here. Alright, so here in pink I've got written down my two equations with the end conditions in there, capital T for t, and then ending velocity and ending position. And what I have right here is a system of two equations and two unknowns, so we can just use some algebra to solve that system using whatever method's appropriate for the system. So for this one I'm going to use substitution. So if I subtract 88 and divide through by t, I get c is negative 88 over t, and then if I plug that into the second equation, I get this. And then if we just simplify this first term on the right side, we'll get negative 44 times t. So the t on the denominator will cancel with one of the t's in the t squared. And then from here it's pretty straightforward. Alright, so we get our t equals 4, so it takes 4 seconds for the skid to stop. So that was one of the things it asked us to find. The other thing it asked us to find is what is the constant deceleration. So now that I know what that capital T value is, I can find what that constant deceleration is. That was our C. And so there's our two values. All right, try some homework problems.